Hello everyone, I'm Warren Yong from University of Twente. In this presentation, I will share with you about a millimeter wave phased array antenna for 5G outdoor base station. First, for why we need 5G communication. Apart from the conventional requirement, which is the enhanced mobile broadband, 5G communication is also envisioned to provide the service toward the mission-critical service and also the massive Internet of Things, such as smart industry and smart automotive. Because of this new application, there is more and more requirement over the broadband data and also low latency. Therefore, in order to achieve this mission, in 5G communication, we are proposed to use the millimeter wave band to provide the service. Millimeter wave band is the spectrum that lies between 20 GHz all the way up to 100 GHz. In 5G communication, we are mainly targeting on the 24 GHz to 40 GHz. Here are some of the examples of the proposed millimeter wave band for 5G all over the world. As you can see, different regions and different countries, they have their different policy and proposal for millimeter wave band 5G. However, this band is usually for between 24.25 all the way up to 29.5 GHz. Therefore, we need some solution that can manage to provide this, that can cover in this frequency band. But why we want to go for millimeter wave band? First, at millimeter wave band, we will have more bandwidth. So as compared to the low RF frequency, millimeter wave band will have like almost 10 times largest bandwidth compared to low frequency. And second, in millimeter wave band, we basically need to use the directional antenna. Because of this directionality, less interference will occur. And third, when we know that when the frequency is getting higher and higher, the RF component will be going smaller and smaller, and therefore we can achieve a much better miniaturization due to the smaller wavelength in millimeter wave band. However, for us to use the millimeter wave band for 5G communication, there are several challenges that need to be overcome. First is the high transmission line losses. As compared to the low frequency, millimeter wave band need to pay a lot more attention in selecting the proper material in designing the RF component and also antenna. Second, unlike in the low frequency band, where the antenna and also the MMIC can be designed and connected through the coaxial cable, in millimeter wave band, the IC and also antenna need to be integrated together. Third, because of the high losses of the cable and also the device, therefore, in order to have these low losses and high quality measurement, this measurement is becoming challenging and expensive. We need also some solution for this. Here are some of the examples of the existing commercialized available millimeter wave phased array. As you can observe, most of these millimeter wave phased array that have been introduced in the industry that employ the simple patch antenna as the radiating element. The main problem with using this simple patch antenna as a radiating element is first, the bandwidth is usually narrow. They cannot even cover part of the 5G band, like the part of the entire 5G band. And second, usually this phased array antenna have the limited scanning. Therefore, the first part of my research is to investigate how we can improve the bandwidth so that the antenna could cover the whole 5G band. And the second part of my research, we are aimed to provide some solution to improve the scanning capability of this phased array. In my project, I propose to use the ME dipole, which is also called as magneto-electric dipole antenna for millimeter wave phased array. This ME dipole is commonly used in the LTE MIMO communication and also designing the millimeter wave fixed beam application. However, it is not commonly used for phased array design. Therefore, in my research, I'm aimed to investigate how this ME dipole can be used for phase array while maintaining its bandwidth. The operation principle for this ME dipole is simple. First, the electric dipole is formed by the fourth patch on top of the radiating element, and the equivalent magnetic dipole is formed by the vias that's supporting this patch. And on the right, we show the structure on how we integrating the MMIC. So basically, we have the 50 ohm termination coming from the MMIC that's shown in the cylindrical bullet that's shown in my pointer, and we design the transition from the MMIC and go into the antenna. By doing this, we can have the full active antenna, and of course there will be a need of the different layer for the DC power supply and also the SPI control for the beamformer. Next is to improve the scanning capability. During our first work, we found out even we have an antenna that can cover 24.25 to 29.5 GHz, but we are unable to find the analog beamformer that can provide such a wide band. Therefore, in this work, we focus on the 26.5 to 29.5 GHz, which is part of the 5G band. However, in this band, we aim to obtain a wide scanning capability. And we propose to use the S-shaped metamaterial as a wide-angle impedance matching layer to provide the wide scanning. By loading this wide-angle impedance matching layer, we successfully to improve the scanning of this simple patch antenna from originally plus minus 50 degree to more than plus minus 70 degree. This project is funded by the European Union through the Horizon 2020 Research and Innovation Program under the Marie Curie grant, which is the WaveComBE project. And I would like to thanks to the WaveComBE Sweden, which is my collaborator, for the help in manufacturing of the antenna prototype. And we would also like to thanks to the NSP in Netherlands for sponsoring our analog beamformer chips for the phase array development. And also the special thanks to Abu Faz, Ariza from WaveComBE, and Thomas Emanuelson, who is my co-supervisor before this, when he is in GapWave and now is in Ericsson, Sweden. And also I would like to thank Xinjin Yang for the technical discussion on the work of the integration of the MMIC phase array. For more information about my research and the details data about my work, you can always visit to my Google Scholar or my ResearchGate. That's all for my presentation today. Thank you.